well, Professor Roger Penrose hardly needs any introduction. He's very well known to theoretical and mathematical physicists from its many fundamental contributions. Let me mention just his work with Steve Hawking on singularities in classical general relativity, for which he won the Wolf Prize in 1988, his twistor theory of gravity, and his quasi-periodic tiles, which have found, I think unlike the singularities, experimental confirmation after the discovery of so-called quasi-crystals in 1984. He's also very well known to a wider public for his fascinating and mind-blowing book, The Emperor's New Mind, which won a Science Book Prize last year. And please don't rush to Naville in town because I bought the last 2 copies. But you can order it. Well, a little over a month ago, we held in the same room a symposium to honor John Bel and his fundamental work on the most basic issues of quantum mechanics. And I'm sure that many of us left the room with a sense of unsatisfied curiosity about those fundamental questions of interpretation of quantum mechanics. So we are doubly happy today that Professor Penrose has decided to include and share with us in his presentation his deep insight also on this subject. Professor Penrose.
Thank you. Well, it's a great pleasure for me to be back in CERN. When I was here last year, John Bel asked me if I would give some lectures this year, and as we all know, John Bel is not with us anymore. I wanted to pay my respects to John Bel, particularly by, in this first lecture, talking about issues related to his well-known theorem. Other things that I want to say will have relevance to him also, but particularly today I wanted to pay homage by describing some ideas which I've actually just had very recently, which relate to his famous result. But to begin with, I want to describe things which are more familiar. In fact, I want to describe the situation that his theorem refers to. It's concerned with the Einstein-Podolsky-Rosen type paradox, or the version which David Bohm describes in his book, where one has a system essentially of the following type, where one has, say, a spin zero object which decays into 2 spin half particles, and these go off in opposite directions, and one then measures the spin of these things in directions, various different directions on these 2 sides here. And the thing is, since the spin of the 2 together must add up to 0, and since, because of the curious properties of spin, you can only measure the spin in one direction, it seems as though the spin, if you say measure this one first, it would seem as though the other one instantaneously must spin in the direction opposite to the direction which this spin is measured to be. Now, the sort of paradox about this is that the direction of the measurement of spin on the left-hand side, that's this one, seems instantaneously, sorry, this time I'm measuring this one first, seems instantaneously to fix the direction of the spin on the right. And this is very puzzling, especially if you think that effects have to propagate more slowly than the speed of light, whereas this seems to have to take place instantaneously. Of course, the question is whether this is anything measurable or just all in the mind or something or other, because the direction of spin of a particle is not something that you are supposed to be able to measure. You can't tell which way the spin is measuring. All you can do is to choose a direction and then see whether the spin is in that direction. and you get some probability related to, I mean, if this is the direction that the spin is supposed to be in according to the theory, and then you measure it in some other direction, and the angle between those two directions is theta, then the probability that you find the answer yes, it is in the measured direction, is given by this formula here, half of 1 plus cos theta, or half of 1 plus the scalar product of these two directions. Well, you see, you might not worry too much if you think somehow the measurement on this side is only telling you something about probabilities of your measurement over here, and you might not think there's anything real about the actual direction in which the particle seems to be spinning. But what John Bel was able to show was that in fact you can dig out of these probabilities something which seems almost paradoxical, that is, that these two particles somehow seem to know something about each other. The state, according to quantum theory, must consider these two particles together as one system, and when you perform a measurement on that system, you have to consider it as affecting the state as a whole, and that whole state involves both particles, so the measurement on one side, the state of the particle on the other side is instantaneously affected. Well, the question is, of course, if that's something that you can dig out something puzzling from, or is it? Well, Bell refers to a thing called, what he called Bertelsmann's socks, which I don't know is familiar to everybody. This chap Bertelsmann was supposed to always wear odd socks, and this is a known fact about him, that he always had odd socks. They were different colors, invariably different colors. Now the thing is, if you observed one of his socks and you found it was red, say, then you knew instantaneously that the other sock couldn't be red. And so there seems to be this effect of traveling instantaneously from one side to the other. But of course we know all the time one of his socks was, say, green and the other one was red, and the fact that you see that one of them is red and you know that he always wears odd socks gives you the information that the other one is other than red, but you don't expect there's some kind of influence which travels instantaneously from one foot to the other. But what Bell was able to show was that the situation here is not like that. There is no way of assigning an individual reality to each of these particles which determines the probability of the measurement. So the point is that you can't have a separate reality assigned to each particle, and that this reality determines, say, the probabilities of measurements in different directions. You must, whatever reality you think these particles have, and I personally, like Bell, consider myself to be a realist, that is to say there is a state, there is something going on which is in the real world. It's not just a matter of doing calculations, and the real world has to be regarded as some kind of non-local state which involves both particles at once. And it is very curious, but that seems to be the way the world is. I want to make a comment first about spin. I'll come back to this later. I've always been fascinated by, well, spin half particularly. I'll come back later to states of higher spin, but here one has a very curious or very direct relationship between these mysterious quantum mechanical amplitudes and real directions in space. And it's brought out most clearly in the case of spin half particle. You see, the general state of spin is a linear superposition of spin right-handedly about the upward direction and right-handedly about the downward direction, with general complex linear coefficients here. And of course the puzzle in quantum theory is that you don't just have a probability weighting of these two alternatives, you have a complex number weighting of these two alternatives. And so one can't think of these weightings as probabilities, they have to be complex numbers, and you can see geometrically the relationship between these arbitrary weightings and the resulting direction. There'll always be some direction in space which this thing is spinning about. That is to say, if you measure it in that direction, then you get the answer yes with certainty. So that direction is something pointing somewhere in space, and it's obtained by taking the ratio of these two numbers here, lambda over mu, if I have it the right way around, plotting that point on the complex plane, the Argon plane, and considering a sphere which has its equator on the unit circle of this Argon plane, and then you project from the south pole to that particular point, which represents lambda over mu, and that gives you a point on the sphere, and you join that point to the center, and that is in fact the direction of the spin here. So one has this clear-cut relationship between geometry, spatial geometry, which, as we know, this geometry of our experiences has 3 dimensions, so we have a sphere's worth of directions, and this sphere of directions is intimately related to the Riemann sphere, that is to say the sphere of ratios of complex numbers, and that includes, of course, infinity, where lambda goes to 0, and if I've got it the right way up, when lambda goes to 0, this point will go off to infinity, and that's when the green line points to the south pole, which is this state here, so I think I have it the right way around. Anyway, so we have a relationship between the complex numbers of quantum theory and spatial geometry. I want to come back to this later on, probably in the 3rd lecture, but for the moment all we're going to use is the fact that we have this probability formula which I mentioned to you before. Okay, so this is geometry and complex numbers. I'll be saying a bit more later on about the relationship between geometry and complex numbers towards the end of this lecture. Now I want to say something about Bel's theorem, and I think the slight generalization of it, and then the generalization of it again given by Bel. But the result is basically of the following type. This is just what I've been describing. You have a spin 0 system, although you could start off in a different state. It's not terribly important, but let's say spin 0 and 2 spin halves going in opposite directions, and then you measure the spin direction in various different directions over here. I won't go into the argument here. Really just to show you here that it's nothing particularly complicated about it. Certainly it's not difficult as mathematics. Just got it written down here. Basically the argument where A represents the probability. See, if you choose a direction little a here, and then you ask for the difference between the probability that you measure the spin, yes, it is in the direction A, and no, it's not in the direction of A, and this is this capital A, and you have another capital B, which is the probability for some other direction B here, and then the lambdas here are supposed to be some hidden parameters, which are supposed to govern what these things actually do, maybe probabilistically, but the whole point about this is, you construct this thing E, the whole point about it is that the A and the B, they can depend on hidden parameters, but they must not depend on what the measurement is on the other side. That is to say, the probabilities for seeing what this thing does, the probabilities for what this particle does, are not supposed to depend on how you happen to orient your apparatus on the other side. If you make that assumption, then you come out finally with this inequality. And the thing is that that inequality is a thing which is violated in actual experiments. It's violated by this probability rule, and I'll come to specific instances to show that. And the implication is then, if you believe quantum theory, in fact, even if you just believe very simple things about quantum theory, this probability rule here, together with the fact that these 2 spins must add up to 0, just those things together, as long as you believe that, then you find that there is a contradiction with the assumption that's gone into this here, namely that the probabilities over here don't depend on the direction of measurement here, and the probabilities over here don't depend on the direction of measurement over here. Seems like a perfectly obvious expectation, but that obvious expectation is violated by the quantum mechanical rules. And the expectation leads to the Bel inequality, which is basically this thing here. I won't go into the details of this because I really want to talk much more about special cases where perhaps it brings out even more clearly what's going on. The point is that the Bel inequality, I think this was the original version he gave here, is violated if you take 3 different directions. Say your A's and B's and C's can be in various different directions. I think I'm taking D equal to B, so the D is the same as the B in this, and A, B, and C are 60 degrees to each other like this, and you just put the things in, and you find that the inequality is violated, telling you that the quantum mechanical rules are not consistent with the assumption that what you do, what happens over here is independent of the choice of measurement here, and what happens over here is independent of the choice of measurement here. Well, let me give you some particular examples which perhaps make this even more striking. The first example is one that was described by David Mermin in Physics Today. So it's just an example of the Bell inequality, but he brings this out in a rather striking way. Here we have the same situation, spin 0 in the middle, two spin halves going in opposite directions, and we are just going to choose three possible directions of measurement on this side and the same three directions of measurement on this side. So A and A prime are meant to be parallel directions, B and B prime parallel, and C prime parallel. And what we're going to do here is these two particles come out in opposite directions, and then while these things are in flight, perhaps, you then decide which of these three measurements to make on the two sides. And the quantum mechanical probabilities have the following two properties. First of all, if the settings are the same, say if this one is A and this one is A, then the results must disagree. Well, that's basically the fact that the spins must add up to 0. See, if the spin here is measured to be in the direction A, then you know this one must, if you measure you set your apparatus up to measure in the direction A, and if you get the answer yes on this side, this one is also in the direction A prime is the same as A, then that means you will get the answer no on this side. So yes on this side means no on this side. No on this side means yes on this side. So the settings are the same, the results must disagree. If the settings are spun at random, so if you just spin these things randomly and do many experiments of this nature, then the quantum mechanical probabilities tell you that the results are equally likely to agree as to disagree. So if you find yes over here, you're equally likely to find yes or no over here. And if you find no here, equally likely yes or no here. They're completely, the total results are equally likely to agree as disagree. And then all you have to do, I won't go through the argument because I've got other things to say, but it's a very simple and elementary argument. All you do is you look at what the probabilities should be, and if you put for the formula theta equals 60 degrees or 120 degrees, you get 3/4 or 1/4. What that means is that if you put that one in the direction A, say, and this in the direction C, then what is it? It's 3 to 1 that you find yes, yes. Whereas it's 3/4 probability that they will agree, and 1/4 probability that they will disagree, if I said that the right way around. But anyways, it's just an application of this formula, and by applying this formula, you will see very rapidly that these things are actually satisfied. But now what this also tells you, suppose you imagine that these two particles here, they may contain some complicated piece of apparatus. You could imagine it's like Bertelsmann's socks, and that right at the beginning, those two things together, each one knew what the other one was doing, and then when they separate, they're supposed to be separate independent objects, like the socks, you see. And then it's supposed to be, if you look at one sock, then that tells you something about what the other sock is. But the point is, with the socks are either red or green, or what happens. And so here you have to imagine that the spin half particle, it might be something very complicated, but it has to decide, when presented with a measurement in some direction, either to give a definite answer or to give some probabilistic answer. That's the sort of realistic Bertelsmann's sock view of what happens, and that's what's contradicted by these two statements here. And it's very simple to see they're contradicted. First of all, in order for these sock-like machines to give 1, this tells you that, in fact, there's no probabilities in the answers, because, you see, if this one here doesn't know quite what to say if you measure it in the direction A, and only is going to give you a probabilistic answer, how is it going to be sure to give you the opposite answer to what this one does if this one happens to measure it in the direction A? So if this one happens to be A, see, it might have been, then this one over here has to know to give you the opposite answer to what this one did. So that means it's got to know in advance what answer to give. So in fact, it has to have prepared answers for every possible measurement here. And then you just go through the possibilities, you see. If this one says whatever its prepared answers to these things are, and then you see whatever these are to this, and it's very rapid, you can see very rapidly that this thing is always violated. So there's no way of forming an explanation of what happens in terms of independent, separate objects. The state of the system has to be considered as something where these two things are part of one extended system. Now, if you want to see the details more, you can look at David Merman's article. Actually, in my book also I give an account of this. There's also a version which I think is due to Stapp, which is just about as simple, if not simpler. And on the one side, you choose to measure in these two directions, either vertical or horizontally, and on the other side, these two directions, which are 45 degrees to the ones you have to begin with. And here the probabilities are, if you use the formula, you find the probability of agreement. You see, let's suppose the actual measurements were this one and this one. I put a yellow circle around to say that this is perhaps how you actually did orient your piece of apparatus. And then you see what your run of, you do it again and again and again, and you see what your run of measurements is. And the thing is, because of this formula, you find that you must only have just under 15% agreement. That is to say, if you get yes over here, then it's only just under 15% of the cases that you'll get yes over here. So if this is a run of observations on the left-hand side here, and this is the run of observations on the right-hand side, you must only have about 15% agreement. And I've circled these in orange here, where they agree. Now the argument is as follows. Now this one over here, how is it to know that the one on this side was to measure in that direction? And if they were independent objects, and if this one was not sensitive to how you set up the measuring apparatus on that side, it couldn't have known that this measurement was to have been made this way. So let's suppose that it might have been made in the opposite direction here, at right angles to this one. And so then there would have been some run where it wouldn't have affected this, you see, if they're independent. It wouldn't have affected this, so we have the same run of yeses and nos, but this one now is some other set. But that differs from this one by only about 15%. So I put little orange circles where it would agree, where the agreements would occur. Now you might say, what about this one? This wouldn't know what this one was doing. This one might have been the other way too, you see. So let's suppose this had been the other way, and then you'd have another run of measurements there. And these would only agree in about 15%. There might be some overlaps, but that just makes things worse. So you've got 15% between here agreement, 15% here, and 15% here. So the total agreement between one and the other couldn't be more than about 45%. But if you use the formula, you find it should be 85%. And so that's gross disagreement. The actual thing, you see, if this had actually been this, and this had actually been this, there should have been 85% agreement, and not just 45% or less. So this shows you that there's an incompatibility between the quantum mechanical rules and the assumption that what you do over here doesn't seem to affect what happens over here. Anyway, these are just instances of the Bel theorem. You might think that you could use this property to send a message from one side to the other. But you can't, in fact. These kinds of correlations between probabilities are just sort of subtly between independence and that amount of dependence which would enable you to send a message. And it's a very curious fact. That's the sort of thing I might come back to later. But I just wanted to give you these various examples. And no doubt people are familiar with the aspect type of experiment which really just verifies the quantum mechanical probabilities, which I don't think, since these are very basic and elementary quantum mechanical facts that one's testing, it would be a great surprise if the results didn't agree with the quantum mechanical answer. On the other hand, it's a great surprise that they do agree, if you like, because it means that there is this essential non-locality and somehow connectedness between separate objects. And in these experiments, you have photons going off in opposite directions. They're not spin half, but they're still two-state quantum systems. The spin might be this way or that way, and you choose different directions in which to measure the spin. and the distance here is something like 12 meters. I think the source is actually spin 1 in this particular case, but that's not important. That's 40 nanoseconds it would take light to get from one side to the other. And the switching time, you see, it doesn't switch until the photons are in full flight, is something like 10 nanoseconds. So the switches, if this is a space-time picture here, and the two photons are produced going in opposite directions, and the decision as to which way to measure the photon is not made until the photons are in full flight. And one comes out with agreement with quantum mechanics, violation of the Bell inequalities. In other words, we have the result that these two objects cannot be considered as independent local things, that somehow there is some mysterious connection between the two all the time. And these things are things I want to come back to later. Now, all the results I've been giving you so far depend on probabilities. Now, there are a number of results of a similar nature where the probabilities can be removed from the problem. And the probabilities that you're talking about are always 1 or 0. So it's either, if you like, certain to happen or certain not to happen according to the quantum mechanical rules. And this, in a way, makes it even more striking, this kind of non-locality. It tells you, in a sense, that the puzzle of quantum theory is not so much to do with the indeterminacy, the probabilistic aspect of quantum theory. The puzzle is much more the non-locality that's involved. Because you have this puzzle already with situations in which there simply are no probabilities. It's yes, yes, and no. And I want to describe a number of results of this nature. Some of them are very recent. In fact, one I want to show you is only just a few days old. At least I think it is. I haven't had time to check the literature to see whether it's in the literature. But as far as I'm aware, it's only a few days old. But before coming to that, let me describe another result. This, I think the one I'm giving is as described by David Mermin again. There are, it arose out of various other Greenberger, Horn, Shimoni, and Zeilinger, I think. And there are Clifton, Redhead, and Butterfield. There are different versions of this thing. The version I'm going to describe, I think, is the one given by Mermin here. And in this version, you have 3 spin-half particles coming from a spin 3/2 state in the center here. Now, it's a little awkward to set up because the spin 3/2 state has to be a special one which has to be prepared in a special way. And that might be a little difficult in practice, but I want to give you later on a way you could do this which would, well, practice I think we're a long way from here, but at least it would give you a way in principle of setting up such a spin 3/2 state. Now what we do is with this initial state, well, I'll actually give you what the state is that you start off with. It happens to be a linear combination of these two, you see, you take totally, I'm trying to bring my pen up in this picture here, that's a little difficult. Imagine the x and y in the plane of what you see there, and the z direction is perpendicular to that plane. And your state is a linear combination of the spin 3/2 being totally in the upward direction perpendicular to that, and the downward direction perpendicular to that. And the point is that what you can do, you see, is you can measure this state. Imagine that these 3 spin-half particles go off in 3 different directions, so you can sit on 3 different planets, if you like. In principle, it could be a long, long way away from each other. And there are measurements that you might choose to perform on these spin 1/2 particle, these 3 particles. And the measurements involve either measuring its spin in the x direction or in the y direction for each one of these things independently. Now, it so happens that if you take the measurement of, say, this particle in the x direction, this one in the y direction and this one in the y direction, that's ax, by, cy, that's what I mean, then this state, the product of these three, has, when I say the product, I mean each one is plus or minus 1. If the measurement is in the direction that you're measuring, I put plus 1. If it's in the opposite direction, I put minus 1. So we must imagine that if it's, well, I have a picture here giving you the different things. Maybe that would be clearer if I can bring that picture up at the same time. This picture is if we choose this first one here. So I'm measuring A in the x direction, B in the y direction, and C in the y direction. And the product of these things has to be 1, that's what it means. This state is an eigenstate of this product. So it's certain that the answer for this product is 1. It doesn't tell you what these individually are to be, but it tells you what the product of them is. And that means that the number of disagreements with these directions must be even. So they might all agree, say, this is this case here where they all agree, right? That's for AX, B, Y, C, Y, that's yes, yes, yes. But if I flip one of them, I've got to flip another one. So it could be yes, no, no. Or it could be no, 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 yes, no, or no, no, yes. So those are the three possibilities. It doesn't tell you which of these possibilities, this one, or this one, or this one, will happen, but it does tell you that the only possibilities are these 4, and not the other 4, which only one of them is flipped from the initial state here. So if I perform this measurement, it's certain that the product will be 1. In other words, it's certain it will be one of these here. If I perform the second one now, that is, I might choose A to be in the y direction, B in the x direction, and C in the y direction. And then these are the 4 different possibilities, just as before. I've just permuted the A, B, and C. Or it might be I choose this one here, which is that. Now the thing is that quantum mechanics, it also happens to be true that if I choose them all in the x direction, then the product must be minus 1. So this is what quantum mechanics says must be the case if I choose them all in the x direction. And you can get this by multiplying these things together. It's just a bit of algebra, and using the fact that these are Pauli matrices, and so they anti-commute. And the anti-commutation property is what gives us the minus 1 here. So quantum mechanics tells us that if I measured them, say, all in the x direction, then I must get no, 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 or no, yes, yes, or yes, no, yes, or yes, yes, no. But I mustn't get yes, 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 or yes, yes, no, anything with an even, no, sorry, I probably said it the wrong way. I must get it so that there are an odd number of no's. I mustn't have an even number of no's. Now the thing is, though, classically, that means to say, if you imagine that these objects were independent things, then they are on different planets, different galaxies, if you like, and this one doesn't know what you're going to do to this one, doesn't know what you're going to do to that one. So it has to be prepared for these 3 answers, and it has to be prepared for what answers it gives, irrespective of the different ways you've oriented these things here. So, but what you can see is that if you look at these alternatives here, and what it really means is I just multiply these things together classically now, without the anti-commutation rule, which gives you the minus sign for the quantum mechanical Pauli matrices, I must give this, which is exactly the opposite of this one. See, it's quite easy to see that it's just a bit of sort of counterfactual argument, like what I did with the Stapp argument before, you say. If this one didn't know what these ones were to do, and it's got to be independent of how these ones do, what these ones do, then you think of all the possibilities here, and you look at them here, and you deduce from those possibilities that it must be this answer here, which amounts to multiplying together these various ones, and you end up with 1 here rather than minus 1. You can run through it, if you like, by saying if this, then this, if this, then this, and so on. I think I won't bother to do that, but you can do it without knowing any mathematics, if you like, just logic. You take these cases here, forget the last one, because that's what we're trying to deduce, and we say, what is the result for these different things? What are the possibilities for the different answers that these things give if they are to be regarded as independent objects which don't know and don't care how you measure, A doesn't care how you measure B and how you measure C. And so what you do is you just look through these various possibilities and you quickly deduce this. And this is completely the opposite of what quantum mechanics says. But what's very striking about this example is that there aren't any probabilities. It's not like the examples I gave you at the beginning, where it was a difference, the probabilities came out wrong. Here, it's just yes or no comes out wrong. Okay. Now, I want to show you something else. This is, first of all, I want to describe something which is older than these results here. 1967, this is the Cauchy-Specker argument, which is concerned with measuring the square of the spin for a spin 1 particle. Now, it so happens that if you measure the square of a spin and not the spin, then you can independently measure the square of a spin in 4 directions at right angles. Sorry, 3 directions at right angles. And the thing is that if you measure 1, I'm using a notation here, what I'm actually going to measure is whether the spin is 0. The m value of the spin is 0 in that direction. The square of the spin is 0, if you like. And that's what I'm saying is yes. And if the answer is yes, I'm going to put a black spot. I'm going to explain these graphs in just a minute. If the answer is yes, I put a black spot. If the answer is no, I put a white spot. And that means that the square of the spin is 1. And the thing is that I can measure in 3 directions at right angles simultaneously, according to quantum theory, the square of the spin of a spin 1 particle, and the 3 directions at right angles have to satisfy this property. That is to say, I have 1 yes and 2 no's. It's got to be like that. In other words, 2 1s, and those are these ones, and 1 0, that's that one. So 1 black spot and 2 white spots. When I join the spots, that means that the directions I'm measuring are at right angles. The spot will represent a direction in space, and if the spots are joined, it means the directions are at right angles. And the rules, in fact, you could say it in terms of a triangle, if you like, that if you have any triangle, that is to say 3 mutually orthogonal directions, then your black spot must be joined only to white spots. You can't have 2 black spots joined together, and because they're, see, that's what I'm saying here, but you can have a black spot and a white spot, and if you see 2 white spots, then they can only be, anything which is connected to both of them must be black. So that's basically the 2 rules here. You mustn't have 2 blacks together. Anything which is connected to 2 whites must be black. And this follows very directly from the fact, the way I think of it, you see, is you're measuring the m squared, and if that's 0, if the spin is 0 in the direction you measure it in, that is what I'm calling yes, and anything orthogonal to that is no. And so orthogonal joins means orthogonal, and you can't have 2 yeses which are orthogonal joined to each other, and anything which is joined to 2 no's must be yes. That's really just the fact that the dimension of the space of the spin 1 states is 2 complex dimensional. Anyway, Cauchy and Specker produced a set of, if I remember it correctly, 119 directions. I'm not sure whether, I still have 117 sticking in my head. It's not going to be very important for what I want to say here, but I think the number may be 119. It's a number of directions in space. You just pick these out very cleverly, such that it contains a whole lot of mutually orthogonal triplets. And then you form a graph of these things. You just sort of join them when they're orthogonal and so on, and then you try and color the spots black and white. And you find that you can't do it satisfying these rules. And that, what that tells you, you see, is if you had a spin 1 particle, and this particle has got to be prepared. So if you choose to slap it, you take some triad, you see, and you slap that triad on the particle. As you perform this measurement, how you do it might be a little bit complicated. Actually, I'll show you how you can do it later on in principle. But it might be, in practice, a bit hard to make this measurement here, but let's not worry about that. You just take some set of 3 perpendicular directions and you apply that to this spin 1 particle. And you know that the particle has got to give 2 no's and a yes. One of those directions is yes, and the other 2 is no, are no. And the thing is that you didn't know, that particle doesn't know what direction you're going to spring on it with this triad, you see, and you might have chosen any one of these 119 directions to just put it on, and it can't have prepared answers for them all at once to be consistent with these rules. So in a sense, that also shows you some impossibility of hidden variables. Well, there's a version due to Asher-Perez of this, which reduces this number from whatever it was then very considerably, in fact down to 33. I should have put the number here. Instead of 119 or 117 or whatever it is, it's 33. You can see as a considerable improvement. He tells us that there's also a result due to Conway and Cochin, where they've got it down to 31. Well, I don't know what their configuration is. I think it's more complicated than the Perez one. The Perez one, if I draw it out as a graph, I was trying to do this last night, and I realized it was hopeless. I need some way of spreading these points out in a neater way. But you have 33 points and all sorts of connections. I haven't quite drawn them all in. The other ones are similar to the ones I've drawn here. I won't explain them, I think, because I want to say something else about it in a minute. But you have connections between these spots, and I've drawn the ones which are connected this lot. Well, there are lots of others which look like these ones coming out here. The rules are not that complicated, but to draw them all in one picture is a little confusing. In fact, I was talking to Perez just last week, and he was explaining to me what these directions look like. Well, the way he was doing it was in terms of a bit of algebra here. You think of these are the coordinates of the directions in space, and this is his paper here, and you take these and then you permute the different axes and you reverse the directions. You can put minus signs in here as well. That gives you 66 actually, but it's really 33 because this direction is the same as the opposite one. And they look like a great mess, like something like that. I'll explain this great mess in a minute. But, well, let me explain more in what this great mess is. Imagine a cube. This wasn't quite how he described it, but this was my way of disentangling this. Imagine a cube, and, well, it's certainly true, it's obvious that if I take directions perpendicular to the three directions perpendicular to the faces, they will be mutually orthogonal. But it's also pretty obvious that if I fix one of them perpendicular to the faces and rotate the others through 45 degrees, so I have one through the face and the other through the edges here, that these will also be mutually perpendicular. So I hope that's obvious. And now what I do is I start rotating this configuration of blue and red directions about other axes of the cube. And I get a great lot of configuration. I also add these purple ones here, which come through the corners. So the directions out through the corners of the cube, through the edges of the cube, through the faces of the cube, and then I start rotating the cubes about the directions through joining two edges here, midpoints of the edges. When I started drawing this thing, I thought, well, it would be nice to see what this looks like, you see. And so I drew it all out, and then when I'd drawn it, I thought, goodness, I've seen that picture before somewhere. And I thought, it suddenly dawned on me where I'd seen it. And this is perhaps rather striking. This picture is probably familiar to you. It's an Escher, and I've always wondered what on earth that thing was doing sitting on top of this tower here. I mean, it's obviously full of paradox, this picture. I thought I knew what this one was. You may be familiar with a little puzzle which you lay to plastic or something and you try and get it apart and suddenly it all falls to pieces on you. Well, that's what this is, you see, which perhaps explains the paradox there, I'm not sure. But what this one was doing, I could never figure out. But evidently all the time, what this was doing was explaining the paradox of reality according to quantum theory. And let me just explain, well, first of all, one can make it a little clearer by using Escher's. He drew this out first, I think. It's almost the same. And then you can try and color the cubes. I don't know if that makes it any clearer. I colored this one too, quite unnecessarily. But you see I've got yellow and orange and red as the three cubes. And this is magnified a bit. I'm afraid it's slightly smudgy, but and there are the colors. I hope you can see them. Or perhaps you prefer, see, there's the red cube. There's the, well, it's green now. That used to be yellow, I think. And that is the one which used to be orange. So you can see the three cubes interpenetrating, and there they are. And here we have the Perez directions. Well, see, what we have is a direction. The centers of the cube, they correspond to these points here. The ones coming out through the corners, so you can see the corners there, various points. Those are the purple ones, I think. And the blue ones are the ones coming out of the edges. Well, there are two kinds coming out of the edges, I think, the green ones and the blue ones. Let me not bother to explain in full detail what's going on there. But anyway, so now we know what that shape was doing sitting on top of the tower in Escher's picture. Well, I want to go on and talk about another way of looking at these things, which will actually lead to a simplification of something of the Perez nature. Well, it involves some other ideas. In fact, it involves an old idea due to Majorana, which was published in 1932, but nobody seems to have heard of it. I described it in various places myself. The result is the following, that if you take any spin n over 2 particle, or the state of spin for n over 2, remember I did this for spin half, and you might have wondered what happens if you take spin greater than half. You see, this is the general state for spin half, can be represented as a single point on the sphere, or if you like, a single direction through the center. So what is the result for spin n, or spin n over 2? The answer is, you take n points on the sphere, an unordered set of n points, and they can coincide, if you like, in various arrangements, and that represents the general state, up to an overall multiplying factor, which we're not concerned with. And if the more familiar thing is you might choose a direction in which to measure the spin, and you find these various different m values. And these different m values correspond to special states where all these points, all the directions upwards or one down and so on, different numbers up and down. Now you might ask, how would you test whether a thing was in a particular state? Well, you can't, of course, measure the state, but what you can do is perform an experiment which gives you the answer yes with certainty only if it is that particular state. And there is a way of doing this in principle, and that is, at least if you're lucky enough, that your state n over 2 can decay into a whole lot of spin halves. Then you can perform the measurements on each of these spin halves in the various pre-assigned directions. And if this original state is n over 2, actually I haven't stated this quite right, I'm afraid. It's not quite as I stated it, because there's a symmetrization involved. I think I better scrap that for the moment. But you can actually characterize these states by saying that if you choose one of these directions and measure the spin in that direction, then the total spin must not be entirely in the opposite direction. So you see, if the upward direction happened to be turned around into this direction, then I can find all these possibilities except the last one. And that characterizes these different states. But I suppose that is a little more complicated. But now I realize one does these things in a hurry, and the thing I said here was intending to say isn't actually quite correct. But it does mean that you could, in principle, look at these well, what one can do, you see, is to look at these Koch and Specker type things. The way I stated it was to choose 3 directions at right angles. But what you could do is instead think of a spin 0, and this goes spin 1 on the 2 sides, and then you make measurements on these 2 spin 1 states. Now the thing is, these measurements would be, say, choosing 3 directions at right angles, which you could do by splitting it in spin halves, but as I say, I didn't have this quite right. I better sort that out for next time. But you can certainly make measurements which will tell you whether the state is in a pre-assigned one of these or orthogonal to a pre-assigned one of these. And so what you could do is do that on the 2 sides, and the trouble with making three measurements at right angles is, you see, what you've got to do is consider, say, two white spots and a black spot for these three directions, and then you choose another one and with one in common. And it's not so clear that if they have one in common, that the color for that has to be the same, whether it belongs to this triad and this triad, because the whole measurement has to be performed all at once. And if you don't believe in quantum theory, so if you believe in some hidden variable theory, then you're not quite sure whether it makes a difference whether you make the order in which you make these things. That's a sort of technicality which can cause a problem with these things. But if you put the version like this, where you choose a direction, you see, and then if this corresponds to one of your spots on your diagram, and this direction corresponds to the spot corresponding to the opposite direction, then you can say if it's in this direction, then it's not in that direction, and so on. I could perhaps come back to this later on, but I don't really have time to talk about that in detail. I do want to say a bit more about the Majorana picture, and first of all, what orthogonality between states means. And well, suppose you've got a lot of red points and a lot of blue points, and you want to know whether the red point set is orthogonal to the blue point set. Well, the way I'm actually thinking of this at first is if I have a spin 0 to begin with, and then this is now spin n over 2 here, spin n over 2 here, and I measure on this side whether it's in the red set or orthogonal to it, and on this side whether it's in the blue set or orthogonal to it, and the orthogonality condition, that is to say, yes, if I get yes here, then I'm certain to get no over here if the following thing is true, and that is whether the following polynomial vanishes. You see, what I do is I construct, these are using the description I had at the beginning, which relates the points on the sphere to complex numbers, that is the point on the Argand plane here. I then form this polynomial. The roots are supposed to be these different directions, and then I have a polynomial, and then I look at these coefficients. I do it again for the red ones, and then I form this combination here. That's really if I want to measure them in opposite directions. But if I want to measure them in the same direction, I have to pass to the antipodal points. I'm afraid I did this rather hastily, and it's probably not as clear as it should be. But if I want to say, for one spin n over 2 state, if I measure the blue points, is that orthogonal to the red points? And the condition for orthogonality is this thing I've written down at the bottom, where this thing is, these are the coefficients of these two polynomials. So it's algebraically, it's very easy to see. But what does it mean geometrically? Well, that's not so easy to see, I'm afraid. But I have looked at the one case for spin 1. Now, you see, any state is described by 2 points on the sphere. They can be coincident or different. 2 points on the sphere. Now, this first condition I wrote down, which is really if I'm measuring them on opposite sides, and it's this polynomial relation here, and that's really why I put it down, is this condition that these points, see, one point measurement is the black ones and the other measurement is the white ones, and the statement is that they should be harmonic. Well, harmonic means, first of all, they lie on a plane, or they lie on a circle, if you like, and such that if I draw tangents to these, then the join of the other two passes through that point. If I can draw tangents to these and the join of the other two passes through that point. That's what harmonic means. But I'm not going to look at the general case of harmonic. I'm going to look at special cases. For example, if it's a square, that's an example of harmonic. So these things are orthogonal to those things if they were at opposite ends. Or this, if I have a reflection, that's a diameter, and then these two are reflected in it. Those are harmonic. But now, if I'm measuring on the same object, I have to pass to the antipodal point, and this is really the only example I need to look at here. Or there are two examples, say this one. This is if I take these 2 points here, that is orthogonal to these two here, because these are orthogonal, and then if I take antipodal points, I flip these over, they're still in the same place, so this pair is orthogonal to that pair. And in fact, this pair is orthogonal to this pair. See, I take these two antipodal points. Well, these, when I say this pair, I hope the picture's clear. It's rather hastily drawn. These are, you measure these are, this is the same height, depth from the center as this two are height from the center, and these are in planes at right angles to each other. Then this pair is orthogonal to this pair. And that is because if you reflect through the center, you get a square. So that is an example where this pair is orthogonal to this pair. Also, I could have taken a special case of harmonic where the two white points coincide and then go to the antipodal point. So this pair is orthogonal to that pair, where these are coincident and they're opposite to one of this pair. Well, that's all I'm going to need in the example I want to show you. So I want to end by giving you another example of a thought experiment, if you like, of this nature, which is simpler than the Perez one, which is just based on one cube now. So I take one cube, and I consider the following possible states. Following possible states. One is given by this axis, that is, the 2 points on the sphere are opposite. That's like in the Koch and Specker thing. I could be measuring the square of the spin in that direction, and yes means the square of the spin is 0. Or I could take them, these are the three axes of the cube. So I have three possible measurements, which is the same as the Koch and Specker situation. In fact, let me give you the diagram. The diagram, remember I had trouble drawing the Perez one. I have no trouble drawing my one, you see. These green spots on the outside correspond to these three axes of the cube. Now the purple spots correspond to a pair of, see, if I take alternate corners of the cube, I get a tetrahedron, and I can choose any pair of vertices. And there are 6 possible pairs of vertices. Those are the 6 edges of the tetrahedron. And those are these 6 spots here. And notice from what I said on the previous transparency, this pair is always orthogonal to that pair. And that's an example of this. So that means the green spot is joined to the pair of purple spots. Any pair of purple spots, this pair of purple spots is joined to that green, this pair of purple spots also joined to that green, you see. So I have this, it's also a triangle because this pair is orthogonal to that pair by what I just said here. See, you reflect in the center and you get the square. So this pair is orthogonal to that pair. And that holds all the way through. And finally, you need double ones on all other corners of the cube. So this one is orthogonal to this pair. That was the example I said here, you see. If there's one pair in common, then it's orthogonal to the opposite one. So this is orthogonal to that pair, and so on. And you get this little simple diagram here. Okay. Question is, can you color the spots of that diagram in such a way, and I hope I haven't got this wrong, or the whole thing will fall rather flat. But let me see if I can remember the rules, or find the rules, it's more to the point. Yeah, here they are. In fact, perhaps I even try and color them, that might work here. What will I take? Another color which we haven't got. Brown will be black and yellow will be white, okay? Now notice that thing is symmetrical. So the rule about the triangle, I can choose brown, yellow, yellow. It doesn't matter which, obviously, because it's symmetrical. Okay. I hope the difference between those is obvious. Maybe not so obvious. And now the thing is also symmetrical enough that I can still, see, I need to have actually I have other colors. It's just that maybe red is better, is it? Red instead of the brown. Okay. Now, I have another triangle here, but the red one has got to have 2 yellows, so there's no question about that. Now here I have a choice, but the symmetry of the picture, if you sort it out, is clearer here. It doesn't matter, it's equally, it makes no difference which I choose here. Now, 2 yellows, I've got to have them joined to a red, and that makes this one yellow. 2 yellows has got to be joined to a red. 2 yellows, that has to be red. Whoops. Well, you see, we run into contradiction. I ran into that rather sooner than I expected, but you certainly do always run into a contradiction. There is no way of coloring the spots in this picture according to these rules. So that tells us that if you chose to measure, and you could do it in a sort of EPR type thing where you had things in 2 directions, and you'd have to find a good way of measuring the state when it's in corresponding to 2 corners like this, which can be done by splitting it into 2 spin half particles, but let me just leave that for the moment, the details of that. And you would arrive at something which gives you, there's no possible model for these things which is consistent with the quantum mechanical results and where these two objects are independent of each other, so that what this one does is independent of how you measure the other one on the other side, and vice versa. And there are no probabilities. It's all yeses and nos, which has to do with these coloring of spots. Well, thank you very much.
Thank you very much. And ready to ask a question?
Oh, so almost a question, was it? We're going to ask?
Yes.
Yes.
It's a question pertaining to the aspect experiment.
Yes.
You said the switching, the optical switching, is done when the light quanta are on the way. How
Yes.
do you know that they are on the way, and when do you decide to switch?
Well, as far as I mean, there are all sorts of different ways you could make this decision. And of course, it's open to questioning in one form or another. For example, you could have some random number generator which makes the decision, but then you might think, well, somehow it already knew what the, depends on what kind of model you have of reality. Could the photon over here be clever enough to know what the random number generator was going to produce? I think in actual experiments, what they have is something like something with little ripples, and it's just all to do with where the ripples happen to be. I can't remember the details of how it's done, but it's done with some physical apparatus, but which has no bearing whatsoever on the type of experiment which is being performed.
So in other words, the emission of the gamma quanta and the switching are independent things.
Yes.
You don't wait until and so on and so on. So you...
Oh no, that's right. You don't wait until something happens. The choice is made by some piece of physical machinery. I think it's water ripples or something like that, and it depends on the random shape of those ripples, which have nothing whatsoever to do with the rest of the experiment. So it would be pretty far-fetched to think that somehow the photon over here was be able to predict what those ripples were going to do on the other side.
Yes?
Probably it's a very simple question because I'm not very good at it. But if you have once measured both parts and then another measurement afterwards which doesn't communicate to the first measurement, can those both be different as long as they don't communicate?
I'm not quite sure I have your question. I mean, certainly there's nothing in the experiments here which really have anything to do with speed of light and all that. I mean, it's just independent things. And it might be that you wait for a long time before you measure this one or not, or you might measure one first. It doesn't seem to make any difference. So it's locality really in a sense, not necessarily to do with light propagation and so on. I mean, that's the way it's usually stated because that's where it's most puzzling. If the effects seem to propagate faster than light, whatever these sort of effects are, as Einstein referred to them as spooky action at a distance. And that spooky action at a distance, these sort of correlations which seem to persist, which are independent of distance, that's one of the striking things about them. It doesn't matter how far away the other thing is, as soon as that person makes his measurement, suddenly it looks as though it's affected what I've done, what it does to this thing over here, which seems rather absurd.
Valentin?
Yes.
I understand that the aspect experiments don't really pardon.
Yes, was there another question? Yes.
Valentin's question.
Yeah.
Okay, since you... Can you
Yes.
repeat the question?
I understand that the aspect experiments don't really violate the Bell inequality because of the poor efficiency of the time.
Yes, I should have mentioned that this is certainly a let out at the moment, that the fact that detectors are inefficient, well, not as efficient as you would like them, means that you could still wriggle around the Bell inequalities in practice. But on the other hand, it's a little hard to accept that that's really what's wrong, because what it means is that if you make you have a beautiful agreement with quantum mechanics, and these points all lie on a curve just wonderfully, and you'd think that somehow if your detectors were made much, much more perfect, that suddenly this agreement would disappear and so on. It's a possible let-out. And it's one reason for looking at this other type of experiment with just yes and no.
Artificially make the efficiency even worse, and it will still hold.
That's right, yes, yes. I mean, it seems far-fetched that that could be really the explanation for what's going wrong, but technically it is a let-out.
Could it also be that nature doesn't permit efficient errors?
Yes. I think that's, I think if you take that view, you're probably going to, I'm certainly with these yes-no experiments, you can, in principle, get away with much less in the efficiency on the detectors, as I understand, and that's what I was told anyway. You're shaking your head. Anyway.
Yes, but it seemed to me that in your argument, at least to my mind, there was a slight discontinuous jump.
Go ahead, yes.
That is following. That in the beginning, you followed the classical route till you came to this Kocher-Specker argument with the absolute magnitude of the spin. Okay?
Yes.
At that point, okay?
Yes.
Then you went over to the Majorana thing, which you represent in a beautiful diagram. Perchance I happen to be familiar with that paper. And then you use that imagery of those points on this Weil or Riemann sphere to associate it with the absolute magnitude of the spin. Now that seems to me a sort of a magic trick.
No,
No, the whole business of the cube had to do with measuring the total spin in three orthogonal directions. That's what you said.
yes, that's right.
Then the Majorana picture, of course, is just an n times repetition of the first argument of the Riemann sphere that you gave. The lambdas and u's are amplitudes for up and down.
No, it's something different. I think perhaps, I probably was a bit rushed at the end. The thing is that the Kochen-Specker argument is concerned only with the square of the spin, which from my point of view would be only looking at those states for which the pair of points in the Majorana description are opposite. You see, that's where m squared is 0, is where the pair of points are opposite. That's this middle case here. Now, what I'm saying is that's yes, and anything orthogonal to that is no. So both at the top or both at the bottom or anything else, linear combinations, is no. Yeah, I probably didn't. I was maybe rushing myself a little at the end. But the thing is, if you think of it from here, these 2 points would be the square of a spin m squared equals 0 corresponds to that state. And anything orthogonal to that is m squared equals 1. Now anything orthogonal to that would be linear combinations of both points here and both points here. But linear combinations could involve, for example, the situation I have depicted here. So I'm allowing myself a little more freedom by not phrasing things in the way that Kochen and Specker did, which was to say take m squared and look at these triads. I'm allowing myself more freedom by taking the Majorana picture and looking at these states generally, where the directions in my cube correspond to things which are not Kochen-Specker measurements. You see, yes, I no doubt I was looking at the clock and thinking perhaps I should, but now you've mentioned it, I could have take this opportunity to clarify it a bit. The green ones are Kochen-Specker measurements.
You could have skipped the entire Kochen-Specker.
I could have, but I thought they were interesting anyway. And I wanted to show the Perez thing, you see, with that picture, which is rather nice. But this is simpler. There's no doubt about it. But it's simpler because you have the freedom to talk about these more general Majorana states, where say the 2 purple spots is a measurement, and any pair of purple spots. The blue one is an ordinary measurement, if you like, but it's not the square of a spin. It's lumping together spin in that direction, and orthogonal to that is either 0 or -1 in that direction. But thank you for allowing me to clarify that.
Any other question? Yes?
Yeah, I'm wondering, if you're treating the spins as a quantum mechanical superposition, how do you justify treating the measurement apparatus as being either in one state or the other state?
I think you're asking a question that might be more relevant to my talk tomorrow. I haven't really said anything about how one performs, well, I mean a little bit here, but that's not the issue here. I'm simply talking about taking the standard quantum mechanical procedures and what results do you get from them. I'll address that type of issue tomorrow. Thank you.
Well, if there are no more questions, we thank the speaker again. Very cute, this cute.